Hello! Let's take a look at example problem 11. Before we do so, if you haven't looked already, take a look at example problem 10, which is problem 3.29 from the text. This problem is extremely similar, so essentially it's the same system, just working in reverse. So we're told that we have 1 mole of liquid hexane at 10 bar, 25 degrees C, that's mixed adiabatically under constant pressure, right? So keyword again being mixed adiabatically under constant pressure. All right. This tells us that our first law energy balance reduces to Q equals delta H. That's the constant pressure term. Then adiabatic means delta H is equal to 0. So in this case, the enthalpy of our final state will be equal to the enthalpy in our initial state. Okay. So determine the moles of the vapor that must be mixed with the liquid in order to produce a final state that consists of a vapor-liquid mixture with 75% by mass liquid. Okay. You may use the data given in problem 3.29. Okay. So I reproduce the data here, and essentially what I'm just going to do is I'm going to work backwards. Okay. So one note here is we're given essentially the quality, right? The fraction of that two-phase mixture, which is in this case liquid, right? So I guess it's not the quality, it's the fraction liquid, right? The quality is typically the fraction vapor. And they tell us by mass, okay? But, do know that whether it's by mass or by mole, it's exactly the same, right? Because, if I have, let's call it XL, right? The fraction that's liquid, that would correspond to the mass of my liquid divided by the mass vapor plus mass liquid, right? The total mass. Now, how do you convert from, moles to mass, right? So conversion factor is just molecular weight. So the mass, right, is just the molar mass or molecular weight times N. Okay, so this is equivalent to the number of moles of my liquid times my molecular weight. Okay, I guess I should write it as a subscript W times my molar mass or molecular weight divided by NV times my molecular weight plus NL times my molecular weight. Okay, so whether you're in a molar basis or mass basis, it's exactly the same. Okay, so we won't worry about the fact that it says mass. We can take it to be moles. So following our last problem, let's work backwards. All right, and what we're going to do is, since we have a system at vapor-liquid coexistence at 10 bar, let's first calculate the molar enthalpy of that system, right? That's 75% by liquid, as specified. Then once we know the enthalpy of our final desired structure or system, then we can work backwards because we'll know the enthalpy that initial system must have. Okay, let's do it. So dealing first with my enthalpy of my final system, I'll call it H2. It's going to be equal to the fraction of my system that's liquid times the enthalpy of my liquid at saturation plus the fraction that's vapor times the enthalpy of my vapor at saturation. Okay. And since XV is just 1 minus XL, I'll write it using that notation. I see. Okay, 1 minus XL times HV sat, right? And I have HL sat and I have HV sat, so I could go ahead and I could calculate that. Okay, so I'm going to assume I have a number. First, I'm going to go through the whole setup, and then we'll go and we can calculate numbers. So once I have the enthalpy of my final system, I know that the enthalpy of my initial system is going to be equal to the enthalpy of my final system. Okay. And the enthalpy of my initial system, right? I'm going to break that up, and I'm going to use same notation as before, right? So I'm going to have some container that contains a liquid, and I'm going to have some container that contains a vapor, and I'm going to mix the two of them together. Okay, and so I'm going to assume, right, that I have some liquid, and I'll just call this liquid state 1. Okay, and in this case, that's going to be at 25 degrees C. So it's at the same pressure as saturation, but it's at a lower temperature, so it's liquid. So it's at, our P1 is equal to P2 is equal to 10 bar. Our temperature of this liquid is 25 degrees C. And I believe we're told we have 1 mole. We have 1 mole. Okay. All right, and then I'm going to have some vapor. Okay, state 1, where P1 equals P2 is 10 bars, so I'm at the same pressure. The temperature, though, is 180 degrees, which is greater than my saturation temperature, so it's a vapor. So it's 180. Okay, and I don't know the number of moles of my vapor phase. All right, so when I calculate enthalpy up here, okay, this is on a molar basis. So when I calculate my initial enthalpy, I want to get things on a molar basis. Okay, and so I know the total number of moles, right, initially is going to be N1L plus N1V, which is equal to the total number of moles I have in that final system. So I'm going to calculate, I'm going to write this as a fraction, all right, where X1L, okay, is going to be equal to the number of moles of liquid. And let me just plug in 1. Right, it's going to be 1 divided by number of moles liquid plus N1V. Okay, and then likewise, X1V is equal to N1V divided by 1 plus N1V. Okay, and the key is going to be, and I'm going to end up getting an equation which is a single unknown N1V, which I'll need to solve. All right. So now when it comes to calculating the enthalpy of my initial system, okay, which is equal to the enthalpy of my final system, okay, I'm going to write this as, I'm going to write this as X1L, right, the fraction by moles that are liquid, times the enthalpy of my liquid part in state 1, plus X1V times the enthalpy of my molar enthalpy of my vapor phase or part in state 1. And so what I'm going to do next is I'm going to calculate H1L and H1V. And so this way I can go ahead and actually I could technically solve for X1L or X1V, since X1V is just 1 minus X1L. Okay, so let's go ahead and let's write out formulas for those so that we can solve. Okay, so now remember when we calculated the enthalpy of my liquid in that starting state, we calculated as the enthalpy of my liquid at saturation, okay, plus CP liquid times, so T1 of my liquid, the final the temperature of my liquid, minus Tsat. All right, so the idea is I know my enthalpy of my liquid at saturation, and so I'm going to calculate the difference between the enthalpy of my state of interest relative to saturation, that reference value I know, so that that difference plus my reference value becomes my desired enthalpy. Okay. And then we had H1V, likewise, was HVsat plus CP vapor times T1 vapor minus Tsat. Okay, so I have everything I need to calculate H1L and H1V. And so then, basically this equation, if I plug in these two expressions, reduces to, and so let me go do that. Let me just go ahead and rewrite this as 1 divided by 1 plus N1V times H1L, okay, plus, okay, now my head's in the way. Let me move my head. Okay, plus 1 N1V divided by 1 plus N1V times H1V. Okay, got it. Okay, so let's jump over to MATLAB, and I will calculate H2, then I'll calculate H1L and H1V, and then we'll get this set up to numerically solve. All right, if you don't want to numerically solve, I could plug in, say, x1v is 1 minus xl, write this out to solve for x1l, and then once I know x1l, that becomes a trivial solution. Right, and it's totally up to you, but let me start to get some numbers that we can work with here. All right, so what I'm going to start with is I'll get my unknowns in there. Okay. So Tsat was 165.7. So T1 liquid, so that was 25. T1 vapor, that was 180. Okay, and I can work with degree C because I'm only taking differences in temperature here, not using absolute temperatures. So let's get HSAT liquid, and that is 22.645. Let's get HSAT vapor. That is going to be 43.4320. Let's get CP liquid. That's going to be 263. Okay, and here it's in joules per mole Kelvin. I'm going to divide by 1,000, just so I'm making sure that all of my terms, right, are using a unit of energy of kilojoules to make sure they're consistent. And CP of my vapor, that is 226.34. Okay, so then to solve for, so we start by calculating the enthalpy of my final state. I also need that x1L is 0.75, or XL. Okay, and so let me call the x2L. So if I calculate H2, H2 is x2L times H sat L plus 1 minus x2L times H sat V. Okay. Okay, so I'd get 27.8137. So H2, all right, just get some numbers to put this in context. It's 27.8137. That's kilojoules per mole. Okay. Then next, let's calculate H1L and H1V. And so I'll make a note that H1 is just equal to H2. Okay, so I'm going to use H1. H1L is equal to H sat L plus CPL times, okay, T1L minus T sat H2 or H1V is equal to H sat V plus CPV times T1V minus Tsat. Okay, and let me not comment those out so I get those two. Let's just run it. T1V, T1L, oh, because I didn't typo that right. T1V. Okay, so we've got H1L and H1V. Enthalpy of my vapor is greater than my liquid. Okay, so got it. So I've got H1L and H1V. And then, again, you could take this by hand, where you could plug in X1V is 1 minus X1L. You could solve for the fraction that's liquid or vapor, and then solve for number of moles. Or you could just solve it numerically. Let me actually work out the math to solve it by hand, just so I don't have to necessarily introduce fsolve or F0 to complicate things on you. Okay, so we had H1 is equal to X1L times H1L plus, okay, I'm going to write this as 1 minus X1L, that's X1V times H1V. Okay, so we'll expand and then we'll collect terms. X1L, H1L plus, we're going to get like a lever rule of sorts, H1V minus X1L, H1V. So H1 minus H1V is equal to X1L, H1L minus H1V. So X1L then is equal to H1 minus H1V divided by H1L minus H1V. Okay. Cool. Okay, so let's solve for X1L. Okay, so X1L is equal to H1 minus H1V divided by H1L minus H1V. Alright, so it's essentially a lever rule of sorts. So X1 is 0.3072. Okay. And then if I come back up here, it's at X1L. So we know X1L is equal to N1L, which is just 1, divided by N1L plus N1 vapor. Okay, so now we should be able to solve for N1V. So let's do it. So this would be X1L times 1 plus N1V is equal to 1. X1L plus X1. Oops, wrong. Sorry. X1L plus N1V, okay, is equal to 1. So let me bring it over here. So X1L N1V is equal to 1 minus X1L, hey, which just so happens to be X1V. And so N1V is equal to 1 minus X1L over X1L. Alright, so N1V is equal to 1 minus XL divided by X1L. Okay. So we find that N1V is equal to 1 minus X1L divided by X1L. So N1V is 2.25 2.2549 moles. And that's it. All right. So N1V is 2.2549 moles. All right. So again, if you didn't look at the last example problem, please do so, because essentially here we are just working in reverse. I could have taken the problem here and solved numerically using F0. It's just, you know what, we can, work out the, resulting expressions analytically, so why not? Let me know if you have any questions.